Let's look at OpenStax University Physics, Volume 1, Chapter 6, Problem 109. As shown below, the mass of block 1 is m1 equals 4 kilograms, while the mass of block 2 is m2 equals 8 kilograms. The coefficient of friction between m1 and the inclined surface is mu k is 0.4. What is the acceleration of the system? So let us get organized here. Let's write down our knowns and unknowns, and then we'll use the diagram and draw our forces on the diagram. So first, we know that m1 is 4 kilograms. We know that m2 is 8 kilograms. And we know that the coefficient of friction is mu sub k 0.4. And we're looking for the acceleration of the system. All right. So let's now start looking at the diagram and drawing the forces that act on those masses. So since we have two masses, that means that we have to look at the forces acting on each one of those. I'm going to start with mass 1. Mass 1 has a mass, which means that it will experience a gravitational pull. So there will be a weight going down this way. Now, as a result of that weight pulling down on it, a block that wouldn't be sitting on a table would fall straight down, right? Well, it's not falling down because this surface is holding it up. So there is a force between the object and the table. That force is called the normal force. It's a contact force, and it's called normal because it's perpendicular to the surface of contact between the two objects. So then I'm going to draw the normal force perpendicular here. So this is going to be Fn, and I'm going to call it 1 because I like to use subscripts for my different masses so I don't confuse the different forces. All right, now what else do we know? We see that there is a string in the problem that pulls this block up. So whenever there is a string, the string pulls away from the object, and that means that there will be a tension force in the string, and I'm going to call that tension force T1. Again, I keep subscript 1 for block 1. We are also told that there is friction in the system, and if the system is going to move in this direction, so the block is going to move up and block 2 is going to move down, then the friction opposes the motion, so that means that the friction force is going to go down the plane. So I'm going to draw my friction force in this direction. Now, we know that we weren't told in which direction this system moves. So it is possible that this mass can overcome the weight and the friction force and make the system going this direction, but it is also possible that this block is going to drag that block up and move down in this direction. So the problem doesn't actually tell me in which direction it's moving. So I just picked the direction being up the plane for this block, down the plane for that block, based on the fact that this is more massive than that. I could be wrong. So how will I know if I'm wrong? Well, I'm going to solve the problem, find the acceleration as I'm asked, and if I get a positive value for the acceleration and a reasonable value, so not in the hundreds of meters per second squared, then I chose the correct direction. If I get a negative value for the acceleration, that means that the block was moving down and this block was moving up. But I'm going to stick with my original plan of saying that this block moves up, that block moves down. All right, so I think I'm done with the forces that act on block 1. Now, block 2, since it's massive, it has a mass, will experience a weight going straight down towards the center of the Earth. So I'm going to call this W2. And it is not in contact with anything, so there is no normal force, but it is being pulled back up by a tension, and I'm going to call this T2. So I think these are the only two forces that act on my system. I will also draw the direction of the acceleration. So I'm saying that the acceleration is up here and down over there. Now, I know that this rope, this cable here, is massless and non-extendable, and there is no friction in the pulley, and the pulley is massless. The problem doesn't tell me this, but these are the types of problems that we're dealing with at this point. We have massless pulleys, massless ropes. There's no friction in here. What that means for us now is that the tension in this portion of the rope will equal the tension in that portion of the rope. So anywhere along the rope, tension is going to be the same. So actually, we know that T1 equals T2. We also know that since the string doesn't stretch, the acceleration of the two blocks is the same. So we know that we have the same acceleration for this block as we do for that block. Now we also have to pick directions. And it is convenient to pick the positive x direction to be in the direction of motion. So I'm going to say that this is my plus x, which means that this will be my plus x for mass 2. Now, if that is my plus x, then perpendicular to it, I'm going to have my plus y. So my coordinate system is plus x along the plane, going up the plane, and down for mass 2 in the direction of the acceleration. So now, since this is so complicated there, I'm going to just draw free body diagrams for the two blocks. And I'm going to start with block 1. So since my x-axis is this way and my y-axis is that way, I only want to draw the forces that are along the x and y axes. So looking at this, I notice that my tension 1 goes this way, and now I'm only going to call tension T rather than T1 or T2. I know that the friction force is in this direction, in the negative x direction, so that is F sub k, 1. I know that the normal force is in the positive y direction, so I call this Fn1. But the weight has components in both x and y directions. So in the y direction, I have this force. In the x direction, I have this component. So if this is my 37-degree angle, then let's try to figure out the geometry here. So if I were to draw a line that's parallel to this line, but up here, then I will have alternate interior angles there that are equal to one another. So I have the 37-degree angle here. So this would mean that my 37-degree angle, which means that this angle plus that angle would make 90 degrees because this is perpendicular to that. And if that plus this is 90, and also this plus that is 90, that makes this angle 37 degrees. So then the y component of weight 1 is going to go with a cosine because it's adjacent to the 37-degree angle. So it's going to be W1 cosine 37 degrees. And the x component here is going to be the sine component. So I'm going to have there, so that's my W1 sine 37 degrees. All right, now I have the free body diagram for mass 1. For mass 2, I only have two forces. I have W2 going in the positive x direction, and I have tension going in the negative x direction. So let me draw my plus x axis. It goes this way. All right. So now that I have my forces broken up into components, I can write Newton's second law. So I know that Newton's second law says that sum of the forces on an object is equal to the mass of the object times its acceleration. Now for mass 1, I will have sum of the forces in the x direction is equal to mass 1 times ax. And similarly, I'll have sum of the forces in the y direction is equal to m1ay. So in the x direction, the forces that I have are tension going in the positive x direction, and I have two forces going in the negative x direction. So I will write tension as a positive force in the positive x direction minus W1 sine 37 minus the friction force, Fk1, is equal to m1 times the acceleration. In the y direction, I have two forces. I have the normal force and I have the y component of the weight. So I'll say that F normal 1 minus W1 cosine 37 equals, and now I know that my object doesn't jump up and down, doesn't move up and down perpendicular to the plane, so the acceleration in the y direction is 0, so sum of these forces is equal to 0. Now, since I have a friction force, there's another equation that I can write. Remember that the equation for the friction force is mu k times Fn. So I have three equations I can write for the block on the inclined plane. Two of them are Newton's second law, and the other one is the force due to friction. Then for block 2, I have sum of the forces, and I only have an x direction, is equal to m2 times a. And now I have to pay attention to the fact that plus x is down, so I have W2 minus tension equals m2 times a. So I have four equations, and I have to solve for the acceleration. So how do I do that? Well, first of all, I will find Fn1 from here as a function of the weight, plug it into there. So then I will have Fk1 is equal to mu k Fn1, but Fn1 is actually W1 cosine 37. Now I'm going to take this friction force and plug it into there. So I will now have tension minus W1 sine 37 minus the friction force. So that is mu k W1 cosine 37 equals m1a. Next, I can take the tension from here. I can solve for the tension and plug it into there. So from here, I know that tension is W2 minus m2a. So I will plug that into here and end up with W2 minus m2a minus W1 sine 37 minus mu k W1 cosine 37 equals m1a. So how about I add m2a to both sides, and I'm going to factor out the a, and end up with W2 minus W1 sine 37 minus mu k W1 cosine 37 equals m1 plus m2 times a. And then when I solve for a, I have W2, so that's m2g minus W1 m1g sine 37 minus mu k m1g cosine 37 divided by m1 plus m2. So plugging in the numbers, m2 is 8. I'm going to skip sig figs and units because I don't have room here. So it's 8 times 9.8 minus m1. So that's 4 times 9.8 times sine 37 minus mu k, 0.4 times m1, 4 times 9.8 times cosine 37 divided by m1 plus m2. So that is 4 plus 8. And when we plug in those numbers in our calculator, we end up with 3.5 meters per second squared. So we lucked out because we got a positive value for the acceleration. When I picked the acceleration to go up, I did get a positive value, which also means that this block is going up. So this is the correct interpretation of the problem. This block goes up, that block goes down, and their acceleration is 3.5 meters per second squared.